Hello and welcome to this use case demo of AI Plan for EU. This use case is from the agriculture domain and it's about silage maize harvesting. I'm from the Agrotech Valley Forum. We are an association of agriculture tech industry companies and research organizations located in the northwestern part of Germany. And we are, together with our members, we are working on the challenges in agriculture and working on the digital and sustainable transformation of the agriculture. We provided the data and the use case, and the technical part was done by the DFKI. DFKI is a German non-profit research institute working on artificial intelligence and the applications of artificial intelligence, and especially we work together with a plant-based robot control department located in Osnabrück, and they are focusing on planning and the applications on planning. The use case is about silage maize harvesting, as I said, and silage maize harvesting is a challenging logistic operation which requires intense machine utilization. As you can see here, first of all you need a harvester, and the harvester needs transport vehicles because the harvester itself don't have a bunker. So in order to operate, the harvester needs to have a transport vehicle around. So you need more than one transport vehicle to reduce the downtimes of the harvester. And the transport vehicle, if it's full, then the transport vehicle drives to the farm where the silo is located and unloads the yield there. And then the yield is pushed into this clamp here and is compacted there. So harvesting is really machine intense, and yeah, for that reason it's the most expensive part of silage production, and the farmer has to plan on the harvesting campaign. He has to set the orders of the fields which should be harvested. He has to select and organize the machines and the operators of the machines. And in case of incidents, for example, the machine breaks, he has to replan and rethink the campaign. So the objective of the planning here is to reduce the harvesting cost by optimizing the machine utilization with a focus on the minimal downtime of the harvester, because the harvester is really the most expensive machine in this whole campaign. Here you can see an animation of the harvest we have done. The pink dot here is the harvester and the other dots are the transport vehicles. So as you can see, they switch, and then when they're full and drive back to the silo, which is located here. And in this situation, you can see there's downtime of the harvesters, and he can only start again when the next transport vehicles is next to the harvester. So it's room for improvement, room for optimization, and this is what we aim for with this planning use case. We use the unified planning framework to find valid plans for our use case, and a valid plan contains first of all the order in which the fields will be harvested and by which harvester. So if you may have a lot of fields, so you need more than one harvesters. And second, the order of the transport vehicles, so which transport vehicle will assist with which harvester in which point of time. And third, which silos will be used to unload the harvest yield in, and this is done for each overloading activity. The planning goals are to harvest all the fields in the campaign, to transport all yield back to the silos, and as an optimization, we want to minimize the duration of the campaign. The main planning constraints are the resource capacities. So the transport vehicles, they are trailers, they have a maximum capacities, and the silos have a maximum capacity as well. As a second main planning constraint, we have this synchronization between the harvester and the overloading transport vehicle. As planning types, we use temporal to using statistic and dynamic action durations to achieve action synchronization. And in sequential planning, we use to internally managing the action durations and the corresponding synchronization conditions. As the engine used in UP, we use Tama with custom heuristics for the temporal and the sequential planning. Example of our temporal planning for 5 fields, 1 harvester, 3 transport vehicles, and 1 silo. So these are this sequence charts of the action of each vehicle. So we have the sequences for each transport vehicle, and at the bottom for the harvester, and the blue action is harvesting in field. So you can see this plan is quite optimal because the harvesters has close to 0 downtimes. We integrated our solution into a visualization, and this visualization is done for real-world scenario. So these are the shapes of real-world fields, the corresponding streets, and also the silo down here. And you can watch during the execution of the plan, you can watch the bunker levels of the trailers of the transport vehicles right here. You can watch the progress for each field, and also you can watch the mass which is already brought to the silo. What is the impact of our solution? First of all, the use case prevents the first step to the use of planning technologies for optimizing agriculture processes. The prototype can generate and inspect plans, but the current prototype is able to do it for a number of fields, but with the current available planners in UP, optimality cannot be guaranteed. So in the future, this could change due to improvements of the UP and new planners. And a future solution could then assist the farmer in the planning of the campaign and of this cost-intensive harvesting, and which can lead to savings in money and fuel consumption. Also, a future solution could assist the farmer to make the right decision in case of incidents. So to know what is the best reaction, for example, to a machine break of one specific machine. Thanks for listening.